Welcome, everyone. My name is Zdarsky. I'm a senior principal software engineer. I'm leading the edge computing team in the emerging technologies group of the Office of the CTO, and my team is actually the one that incubated MicroShift. And with me today is...
Hi, I'm Jon Cope. I work with Frank and worked with him in ET, and up until recently, I transferred over to the OpenShift engineering side of things following the MicroShift into productization. And I'm a software engineer.
All right. So I hope you didn't miss it this morning when Red Hat sent a press release announcing the new Red Hat Device Edge. And that Red Hat Device Edge actually contains MicroShift. So this is why I want to talk about it today. And before, John talks about the details of MicroShift, remember the talk of the Locky team, right? Matt and Ian earlier today, right? That's, we are collaborating with that team. We were collaborating with the team, and we're continuing to collaborate to actually make MicroShift possible and also meet our customers' use case, because that's the model that we typically use. And so let me unbox a little bit on what is Red Hat Device Edge. If you're looking into edge computing use cases with OpenShift, you've probably seen, that, for example, BMW in Germany does edge computing where they're doing drive simulations to train their autonomous cars models in OpenShift clusters, right? You have single node OpenShift deployments with Verizon running 5G base stations. But there's this whole class of use cases that we did not tap into. And that's what we're doing with Red Hat Device Edge, right? And it's this use cases that you see here, right? It's the drones that you've heard about earlier. It's about satellites. So Aaron Boyd this morning mentioned that MicroShift is actually in space right now on a satellite. We have use cases with IoT gateways and these very small 5G radios, similar to the one that you see down there. And why are these types of use cases different? Well, that's because we're talking not about servers in a controlled environment. We're talking about field-deployed devices. What does that mean, right? We're talking about devices and their embedded compute unit. And these compute units are not server hardware. There are single-board computers and systems on chip, and you buy them because they are optimized for a certain class of applications, like running machine learning models, like doing signal processing, like doing media processing. And they come with all the I/O that you need. They come with all the accelerators you need, whether GPU, TPU, networking accelerators, video encode, decode accelerators, but they're rather limited in resources, right? So you get like 8, 16, 32 gigs of RAM, small number of CPU cores, and unlike servers, they are then not extensible or not really extensible. The other part is that a lot of that hardware actually does not support a lot of the highly standardized hardware and firmware features that you would find on server-grade hardware, right? They're implementing it differently, and that's a problem for the operating system when they're trying to light up the components on that hardware. The other aspect comes from field deployment. So you can imagine in these use cases that you've seen that there are additional engineering constraints in terms of power you need to consider. Battery power, solar powered, power being unreliable, failing at any moment in time. Or that you have constraints on the thermal design power, right? You don't have cooling, especially like in space. Or networking constraints. You may not have any network at all. It may be intermittent, it may be slow. You may pay for it by the megabyte, right? Thinking about satellite links. It is not a network environment that you control, unlike most server deployments. And finally, of course, security. What happens if you don't have any physical access control to protect these devices, right? The next challenge is the expectation of the deployment model. Ideally, what we want to do is hardware supplier send it directly on site rather than to your central IT where you install something and then ship it out, right? It's more like the Wi-Fi access point that you buy. You unbox it, you plug it to the wall, you plug it into Power over Ethernet, and you walk away. Right? That's the expectation of the provisioning model. And finally, on these devices, you don't have any out-of-band management mechanism, right? So there's no IPMI, there's no, in most cases, no human that can actually fix stuff when they break. There's no management network. And so these are challenges. Another challenge is that a lot of companies from the systems, embedded systems space, they're used to very different tool chains, like building basically the whole system from source using Yocto or Buildroot tool chains, right? So very far away from containers and Kubernetes and all that stuff. Okay, so let me unbox the Red Hat Device Edge. What we're actually doing is we're releasing a Red Hat Enterprise Linux. Surprise, right? It's an enterprise Linux with a small footprint, and it's not based on a package-based, but on an image-based model. Plus, it contains several new features and tools developed for the device edge, right? And of course, reusing some of the features that we see in other flavors like RHEL Core OS. It's image-based. Why? Because think about your phone, right? You're not downloading individual packages. Vendors are creating an image of the whole system, operating system kernel applications, baking it into an image, and then you version, you build, you test, you roll the whole system out as a unit. Right? And of course, what we want to do is make it easy for you to roll your own operating system, right? Build the drivers that you need into this. Leave out other stuff, add an agent. And for that, there's tools like Image Builder that allow you to do just that. It's also designed for ADB deployments. So what happens when you download an update, obviously you want to, what you can do is you download it into a parallel file system, right? You stage the data, and that moment, network can fail, but your updates will still be safe because this new system is in parallel. And you then just basically flip a pointer and then reboot the system, and then you automatically come up with the new version. Or you flip the pointer back, you reboot, and you're back at the old version, right? It's an AB parallel system. And that's very efficient with Delta updates. They have what's called green boot health checks. So like you used on Kubernetes with your containers, you define health checks telling the system, did it come up healthy? And if not, automatically roll back. There's the FIDO device on board, which is an industry standard that's basically ensuring that you get a late binding between device and owner. You plug in the device, it discovers its owner, it will onboard with the owner's management system, and then basically receive its initial credentials and identity. And finally, this Red Hat device has been built for RPM, container, and VM workloads. Plus, it contains MicroShift, so you can also do Kubernetes workloads in the same model. And why would you want to do that? Well, we've heard it already from several of our customers this morning, right? Because you start with Podman, lots of tiny little pods, right? But as you grow, sooner or later you need orchestration. Then you may want to start scripting something, but that's not a good idea, right? Because Kubernetes is the de facto industry standard for orchestrating containers. Or you may be standardizing on the Kubernetes model for software lifecycle, for deploying off-the-shelf Kubernetes workloads. Or you may want to standardize across cloud and the farthest edge your software development and operations. And potentially, of course, you want to grow, right, to more nodes or to HA. And with Kubernetes, you can do that, obviously. You all know this. So again, in the Red Hat Device Edge, we include MicroShift, what is Jon will talk about. But the key point here is it also supports different models. You can use it, the RHEL Device Edge, as a container host and dynamically deploy and undeploy and change your workloads on top. Or you can bake your container applications into the system image. It's like on iOS or Android. You have your applications delivered by the vendor, your core applications, and others you download from the App Store. And those are the models we want to support. To you.
All right, my notes are about font size 2, so I'm going to do it off the sides. So this is where OpenShift comes in. As Frank said, users need to be able to run containerized workloads at the edge in an orchestrated manner. OpenShift is great for running orchestrating containers, but it's good for doing it in a data center on bare metal virtual machines. But it's not as great on a resource-constrained device. That's where MicroShift comes in. We took OpenShift. Or rather, took all the best parts of OpenShift, all the ones that were pertinent to the edge, condensed them down, and turned them into a single single binary deployable as an application on top of the operating system. I'm trying to remember my notes. Yeah. So one of the key things to remember is that MicroShift is OpenShift. It's not a flavor of OpenShift, and it's not a sort of side variety of it. It's built on OpenShift bits. It incorporates core OpenShift and Kubernetes components inside it. So what I mean by that is, oh, apology. I'm getting ahead of myself. Before I get into that, we also, we don't just mirror OpenShift into MicroShift. We build MicroShift in the same pipelines that we build OpenShift in. We test MicroShift in the same pipelines that we test OpenShift in. This to us was critical early on, and it paid off in that we are now able to keep pace with OpenShift releases and catch regressions and incompatibilities early and fix them quickly. A second thing that we are benefiting from the OpenShift CI is that we need to be able to rebase onto the OpenShift bits quickly and at the same tempo that they release, typically nightly, to follow the Z-stream releases. Y-stream releases are more complex and usually require some hands-on by an engineer. To handle the rebasing, Frank wrote a very complex automation script that can take in a version of OpenShift, pull down the OCP release image, dereference the actual commits for each OpenShift component source code, and then rebase MicroShift back on top of that. So we'll vendor in core bits of OpenShift and pull down the container image digest for the small set of service or cluster services that we host on top. Can you slide me, please? So this is a bit of a diagram of what this looks like. Given a Z-stream release, we will pull in the OpenShift source code and vendor it independently or discretely per each component. That covered in the MicroShift binary in the bottom. So all that's compiled into a single binary, run as a single application. We also pull in these component manifests, which we embed as binary data. Those manifests define our cluster level services. Noted on the right here, Service CA, OpenShift, DNS, et cetera. I'll get into those a little bit more later. And then we're able to quickly build that and turn it into an RPM, which can then be turned into an RPM OS tree layer and delivered to devices. So speaking more to the architecture of MicroShift, we spent a lot of time trying to redefine the OpenShift paradigm of high availability, scalability, and the ability to just maintain thousands of workloads at a time. What we came up with was a very small binary. I think we said at roughly half a gig. And inside that binary, we execute etcd, the Kube API server, Kube controller manager, the scheduler, the kubelet. From OpenShift, we run the route controller, the policy controller, and a couple of specialized controllers that we wrote. Well, I say controllers, but services that we run to ensure that we can deploy additional CRDs and our CNI and CSI plugins. In addition to this, so because MicroShift runs as an application, it stores its cluster state on the host machine, not in config maps or in dynamically provisioned volumes on access through PVCs. This gives us a couple of benefits. One of them is that we can continually restart MicroShift without damaging the cluster or interfering with runtime applications. This is really useful when combined with our support for offline images and offline manifests. In particular, offline manifests can be delivered to directories that we've defined in MicroShift, where a user will place their manifest as customized YAMLs. And then on start, MicroShift can pick those up and deploy them on the cluster right away. This means that you can deliver them as a OS tree layer after deploying MicroShift or at startup, reboot MicroShift, and within seconds, your workload will be deployed. Combine this with like over-the-air updates from Fleet Manager, and you're able to push out workloads from a central location to these devices and be confident that the cluster will start, and if it can't start, if there is a greedy workload that crashes the system or is just malconfigured, we can rely on Green Boot to roll the system back and preserve the cluster state and maintain the workloads. I do want to note, though, that Green Boot will not save your workloads. If your workload is broken, it will have to be repaired. It's just not something that Green Boot does. Slide, please. So packaged with MicroShift, we've included a CSI driver and a CNI driver, and we spent some time, a significant amount of time, researching these and really trying to narrow it down. There's a lot of variety and a lot of solutions out there, and based on partner feedback, we landed on ODF LVM by Red Hat, which is the operand for the LVMO operator. ODF LVM is really valuable from a deployed device standpoint because thanks to deploying RHEL underneath it, we have LVM built in by default. This means we can protect the operating system from greedy workloads that get out of hand writing data to the system, and ensuring that they can't crash out the device by just dumping all their data. Secondly, we also protect them from each other. So a workload can't interfere or access another workload's data without express configuration from a administrator. And the last thing that brings with us is the ability to, ODF LVM comes built in with snapshot support and is capable of preserving enough space on disk to store your snapshots, guaranteeing that, ensuring that workload requests can't starve out any support for snapshotting. On the networking side, we opted for OVN Kubernetes, which is an upstream version of OVS, which is another Red Hat component, and well supported and well used. So it's a high quality, highly trusted technology. It also ensures workload isolation at the networking layer and satisfies partner needs for multicast and UDP. So with a minimalized OpenShift, what we're down to now is a container orchestration platform with security, workload isolation, safe update and rollback procedures that can run on two cores, 2 gigs of RAM, and just 16 gigabytes of disk space, which leaves plenty of overhead for user workloads. And we've also done this without sacrificing the pertinent and important parts of OpenShift, which is at the device edge security. So we still include the controller for security context constraints, and we still support routes and ingress. I'll note, too, that those are the only OpenShift APIs that we incorporate into MicroShift. That's because MicroShift is very narrowly defined for the edge. We made the choice early on not to try and solve every problem with MicroShift. MicroShift is not designed to be a CI/CD mini node or a desktop developer environment. It can be used as that, but that's not something we support. And to that end, we were able to remove we were able to narrowly define the scope and thus cut down the size pretty significantly. So the next thing is, how do you manage hundreds or thousands of headless devices deployed in a factory or deployed out in the field, often installed and maintained by non-technical personnel, and perhaps in remote locations? Well, OpenShift would have solved this internally. It manages its own system, it manages its own machines. It's capable of provisioning, cloning, and transferring workloads between nodes. MicroShift is a single node operation and does not interact with the host system in terms of control. It doesn't it doesn't specify system configs, machine configs, and most notably, which I shamefully almost forgot, does not deploy Red Hat operators. There are no operators in MicroShift. And that was a deliberate decision early on as well. There's no need for an operator if your machine is a single node, if it's already got lifecycle management at the system layer, and it can be managed remotely with on an atomic operating system. So to manage these devices, we are leaning on more tried and true Red Hat technology. At the system layer, Fleet Manager will enable users to push out workloads from a singular location out to 1 to N connected devices, and be sure that those are either going to perform an update safely or roll back if they can't report otherwise. At the Kubernetes layer, we're able to also push out manifests directly when connected to ACM, barring, of course, any APIs that we don't support. So this is typically your core Kubernetes workload definitions.
Right.
There's a lot more to cover, but there's simply not enough time for that.
Yeah. So just to summarize, I hope what you take away is that this device edge is a very different class of edge computing use cases, and that with Red Hat Device Edge, we actually want to expand where you can use Red Hat platforms to this class of use cases. And the way we do that is actually addressing these challenges that make the device edge unique through an operating system that has all these features enabled and changed to an image-based model, right? Because we believe that this is a time-proven way, actually, of operating large numbers of devices. And with MicroShift, we basically said, let's not reinvent a lot of stuff that the operating system shall do. We just rely on these rail capabilities and then layer on top this RPM that you can embed into your OS trees. If you want, you can embed your workloads into those OS trees and then treat everything as an image-based model. And just very briefly to clarify that it doesn't get misunderstood, when you said operators, I just want to qualify that's the operators that manage the operating system and the configuration or server-specific hardware, or basically a multi-service cluster. Obviously, your application operators would still continue to run. So just wanted to make this distinction. Right. Thank you very much. And I'm not sure we have time for a question.
Thank you.
Testing. There you go. We do have one question from the virtual audience. I'm going to read it off and see if I get all the acronyms right. Does MicroShift have a load balancer? And can you allocate an SVC with a type load balancer? Does that?
Right now in the what? So right now, until 4.12 comes out, and we can actually officially release the RPMs for MicroShift. You still, of course, have the option to go to the site, build stuff from source. We also provide community-built RPMs for that. In the current version that you don't know, we do not have the inbuilt service load balancer. You're using node ports for that, or you're deploying the Metal LB load balancer on top. That's a very simple operation. It's documented, and then you get the service load balancer. We do intend actually to provide a slightly more compact and small footprint version of load balancing that one of our MicroShift customers asked us for. So that will also be available, but not in the current version you can download.
Not yet, but soon. Okay, awesome. Is there a question in the back? Here, hang on a sec.
Hello.
All right.
Is there an etcd pod? Whenever they do a demo for MicroShift, we never see etcd pods. So how does etcd run in the cluster?
It's part of the core MicroShift that's basically running as a systemd unit. So you say, system control start MicroShift, and will automatically. Can't go back. Automatically start like the whole control plane, including etcd, and run that on the host. And what you see running as pods are those hosted services which we will partially make also optional, like OVNK, Topo LVM, the OpenShift ingress or the router, OpenShift DNS, and the service CA. Those are deployed on top of MicroShift.
MicroShift binary is what's actually running the etcd.
Yes. Yes.
All right. Is there any other questions? All right. Annette? Here. Can you use the microphone just for a sec, just so it gets recorded? Thanks.
Hi. Is this called, not sure it's on, a single node OpenShift?
No, it's not.
Okay.
Single node OpenShift. Well, OpenShift has a couple of deployment topologies, right? By default, you separate the control plane into dedicated machines from the workers. There's a topology called 3-node compact clusters, where you basically collocate those in order to just run on a 3-node HA footprint. And then there's single node OpenShift, which is basically your OpenShift, but just running on a single machine. It also has additional tunings to basically constrain the CPU footprint to a single core. But all of that is plain OpenShift. That means you can use exactly the same processes to manage the workloads, the cluster, the operating system and configuration top down, right? MicroShift is a very, very different model because we're basically using a different flavor of RHEL, if you want, not RHEL Core S, but this RHEL for device edge. That's built towards the device edge model. And MicroShift is an RPM that you basically DNF install MicroShift, and then you have your running cluster. The consequence is that this MicroShift cluster does not manage the configuration because in this device world, the system builders want to take control of all of this operating system, right? It's what Colin earlier on called like exposing, all the Linuxy part, which OpenShift conveniently abstracts from.